a little flame, dum-dum, and a few grains of sodium. Oh, hello there. Well, now let's see, where was I? Oh, yes. Oh, my. Oh, what could I have done wrong? Well, no wonder. I was supposed to use grams, not grains. Precise weight or measure is very important in science. A little too much of this or not enough of that and, well... Excuse me. As I was about to say, precise weight and measure are important in man's daily life, too, and has been for centuries. Before man had a system of weighing and measuring things exactly, he could not be sure when things were too short. He had no way to determine when things were too heavy. He had no way to gauge when things were too narrow or too wide. He had no way to judge when he had too much, or even when things were too hot. He just had no way to measure anything. Things that we take for granted, the size of an axe or the length of a spear, had to be developed by early man without the aid of measuring sticks or guides. But these primitive estimates were not as reliable as exact measures. Guesswork could not accomplish the task. But with trial and error, man fashioned workable tools. Another man then copied this standard to make his tool work. Well, you can't argue with success. I even made mine the same length. Oh, no! Yes, well... Sometimes the original standard of measure was lost, broken, or damaged beyond repair. But little by little, man became more clever at his attempts to make standards. When there was a job to be done, a leader usually set a standard for all to follow. If the leader cut a beam to the correct length, it was simple for the others to follow the standard. The others could simply follow the leader by using the same number of arm spans. But one man might have shorter arms than the leader. And unfortunately, this system didn't always work. Using arm span measurements was fine, but arm lengths might vary. But as man's need for standards of measure grew, his ingenuity gradually took hold. When the Great Pyramids were under construction in ancient Egypt, a standard measure was essential. The Egyptian builders used the cubit, which was the distance measured from the tip of the pharaoh's elbow to the tip of his middle finger. In this way, each pharaoh or king set the standard for groups of workers to follow during construction. Only by using such a master standard, the length of one man's arm, could each worker get those huge stones to fit precisely. The ancient Greeks had their own system of measurement, too, the most common of which was the length of a man's foot. For dry or liquid volume, the Greek standards were made of pottery. And when Greece was conquered by the Romans adopted most of these same standards. The Romans also developed their own system based on the uncia, their inch, of which there were 12 to a foot, and the mile, which was originally 1,000 paces of a Roman soldier. Finding a uniform standard to communicate to others could not have been an easy task. Crude copies made from the first standard were usually inaccurate, and errors became even greater when copies were made from copies. And, of course, by using such a crude tool day after day, it became worn. And the end product did not always come out the same. So, as we can see, man may have had standards of measure, but the materials these standards were made of were not very reliable, and often were difficult to move from place to place, or keep from being damaged. Whoops! While he was learning about measurement, he was also developing a common means of weighing objects. He probably lifted similar objects in each hand at the same time and found that one was heavier than the other. Through trial and error, man found that a balanced load was easier to carry. And that led to his discovery of the scale. And this principle became very handy when he began to barter with others. But here, too, he ran into trouble because the standard used to weigh something might be different in different communities. And there were different standards for different goods. How very confusing to use one set of weights for measuring gold and another for measuring fruit or grain. And the list of different standards is almost endless. For special units of length and weight, there were the line, the tail, the tally, the link, the fathom, perch, pole, chain, furlong, cable length, rod, ulna, medium foot, gad, quarantine, league, pace, palm, hand, yard, foot, inches, the mina, the stone, talent, shekel, cat, sack, clove, cauldron, butt, pipe, firkin, stake, summa, ton, long ton, short ton, avoirdupois, crown, point, troy pounds, pounds, and brains. Oh, no! Well, what a mess. About the time of the French Revolution, science began to grow and demand more precise ways of communicating weights and measures. French scientists measured a certain portion of the Earth's surface, divided it into standard lengths, and defined the meter. They all agreed, after looking into the problem, that 1/10,000,000th of the distance from the pole to the equator would set the standard for the meter they would work from. After they agreed upon the meter, weights and volume measurements could be established, which they were. The standard measure for weight became the gram, and liter came to be the liquid or dry material measured. While the gram was the standard used for measuring small amounts, the kilogram, 1,000 times the size of the gram, was used for larger amounts. Precise samples had to be made and put into the archives for safekeeping. It was a good way to set an example and encourage others to use the system. But most importantly, they made these samples very accurately and from a material that was highly resistant to corrosion, platinum. Platinum was ideal for its purposes. It was a stable metal. It would not expand and contract during temperature changes, which meant it would stay the same size. And platinum couldn't easily be coaxed out of shape to shorten length or decrease volume capacity. Finally, in 1799, after thousands of years of error, argument, and chaos, permanent standards were achieved. And although the metric system was not adopted immediately by every country, it was eventually accepted throughout the world as the first international standard of measurement, and for good reason. Metric arithmetic is simple. It is based on multiples of 10 as a guide for measuring distances, length, weight, volume, or temperature. The length of something, or the distance along a line, is measured in meters. For instance, a door is approximately 2 meters high. And if we want it to fit a space exactly 2 meters, we can make it exactly that, 2 meters. But if we want to measure a smaller distance, like the width of the door, the meter is too large a unit. Because the meter is broken up into 100 equal parts, we can measure a shorter distance without any trouble. So, we are now measuring in 1/100th of a meter, or, since centi means 1/100th, in centimeters. The door is 81 centimeters wide. To measure the thickness of the door, we must use even smaller units of measure than centimeter, because centimeters are not small enough. Now, the meter can also be broken up into 1,000 equal parts, and we can measure a much shorter distance. Milli means 1/1,000, so we are now measuring in 1,000ths of a meter, or millimeters. The door is 33 millimeters thick. As we have seen, 100 centimeters make a meter, and 1,000 millimeters make a meter. It's simple. Centi means divided by 100, and milli means divided by 1,000. But now my problem is that if I want to measure how far it is to the next city, or across town, say to my brother's used bookstore on 18th Street, the meter is too short. A long distance like down a street or along a highway would require too many meters. I need some unit of measure longer than a meter to describe the distance. Here we multiply the meter by 1,000 to measure the longer distance more conveniently. Kilo means 1,000. So we are measuring 1,000 meters at a time, or kilometers. My brother's bookstore across town is about 4 kilometers away. Just remember that for measuring length or distance along any line, use the key unit meter. For small distances, use millimeter and centimeter. And for long distances, use kilometer. If we want to measure liquid using the metric system, the key is liter. 1 liter is the contents of a cube exactly 10 centimeters on a side. The form surrounding the contents or the shape of the container may vary, but the contents will always measure the same. 1 liter is also a little more than the contents of 4 small bottles of soda pop. But to measure 1 bottle, we need a smaller unit of liquid measure. For that, we use milliliter. Just as before, milli means 1/1,000th, and we are now measuring in 1,000ths of a liter, or milliliters. 1 small bottle of soda is a little more than 250 milliliters. Multiply liter by 1,000, and we have kiloliter. Kiloliters are used for measuring really large amounts of liquid. Don't forget, for measuring liquid, use the key metric unit liter. For small volumes, use milliliter. And for large amounts of liquid, use kiloliter. Now, for measuring weight or mass, we use another metric unit of measure, the gram. A paper clip is about 1 gram in weight. But if we want to weigh a tiny pin, we need a unit smaller than a gram. So, we divide the gram by 1,000 and use the milligram. That's right, we're using milli again, or 1/1000th of a gram. Of course, for weighing things larger than pins or paper clips, such as people or fruit, we need a larger unit of measure. We just multiply grams by 1,000, add kilo again, and get kilograms, or about the weight of 5 medium-sized apples. By the way, 1 kilogram is the weight of 1 liter of distilled water at sea level. Keep in mind, the key unit for metric weight or mass is gram. For very tiny amounts, use milligrams. And for heavier objects, use kilograms. Now, this just leaves one more thing for us to cover. Temperature. In the metric system, we use a thermometer measured in Celsius, named for the man who invented the metric thermometer. The Celsius thermometer is also based on tens. 0 degrees Celsius is the temperature of water when it freezes. Normal body temperature is 37 degrees Celsius. And 100 degrees Celsius is the temperature of water when it boils and turns to steam. Oh, my. Oh, no! Well, I'm certainly glad that's over. Now, the important thing to remember is that in the metric system, meters are units for measuring the lengths along a line. And depending on how long a line we want to measure, we can use either centimeters or millimeters for short distances, or kilometers for longer ones. Liters measure liquid volumes, and milliliters are used for smaller quantities. Kiloliters are used for very large volumes. Grams and milligrams are used for measuring smaller weight or mass, and kilograms are used for weighing large objects. And for temperature, we use Celsius. Now, all of these metric measurements are based on a key unit. And these can either be broken down into smaller units for measuring smaller quantities, or they can be multiplied into larger units to measure larger quantities. The use of tens, 100s, and 1000s makes it all very simple. There are quantities and units that we haven't talked about, and some others very important to science and engineering, but you can investigate those yourself. And that's basically how the metric system works. And now you can make it work for you. You may even find the metric system helpful when doing things like building a home for some of your little feathered friends. Oh, my goodness. Here we go again.